This is Ms. Martinez, and in this unit we are looking at section 5, which is titled Product and Quotient Rules. These are the rules for finding derivatives of functions that are expressed as products or as quotients. So, our objectives. As a student, I'm looking for you to be able to find the derivative of a function using the product rule, to find the derivative of a function using the quotient rule, and to find a higher order derivative of a function. So let's get started. I want to define for you what the product rule is, and in your notes, please write it as you see here. I think it will help you to remember it the easiest and work with subsequent rules as well. So, what is the product rule? If a function is a product of two different functions, then the derivative is going to be the first times the derivative of the second plus the second times the derivative of the first, which I have expressed here as the derivative of f times g plus f times the derivative of g. You'll see it's fg, fg. Both of those functions are being multiplied, and in each case you take the derivative of one of the functions. The first time the derivative of f, the second time the derivative of g. And if you set it up this way, like I have written, which is contrary to what you see in your notes, it means the same thing. It's just written a little bit different using kind of a pattern here. I think it will make our next rule easier to use. So let's practice. We want to find this derivative. And that would be the derivative of the first expression times the second plus the first times the derivative of the second. The derivative of 2x minus 1 is just 2, and then you'd still be multiplying it. And then it would be 2x plus 1 times the derivative of the second x function, and that would just be 1. So simplify here, multiply, and then combine like terms, and that would be your final answer. Now, of course, you could have taken the function f and multiplied it to find what the product was and then take the derivative, but this is a different approach, and in some cases this is going to be really the only approach that you have. So let's look at another. All right, now on this one, I don't want to have to multiply all of that. I think that finding the derivative is going to be easier done when you just take the derivative product rule. So that's the derivative of the first times the second plus the first times the derivative of the second. If you want to pause the video and go ahead and find those derivatives, that would be a good thing to do right now. You should have 2x plus 3 times 2x squared minus 5. And the same as before, x squared plus 3x minus 1 times, that derivative would just be 4x. Now we're going to do some distribution, and if you want to pause the video and do that, go right ahead. You should have 4x cubed minus 10x plus 6x squared minus 15. And then that second part would become 4x cubed plus 12x squared minus 4x. And combining like terms, you'll have 8x cubed plus 10x squared minus 14x minus 15. And that would be the derivative of your y function. So that is using the product rule. Another rule is the quotient rule. And you'll see that it looks a lot like the product rule. Look at your numerator. It looks the same, other than the operation between your two is now subtraction, and you're dividing by g squared. I like to write them this way, which I know is contrary to what you see in your notes, so I would encourage you to write it as I have done, because then I don't have to memorize a whole bunch of different setups. They're kind of all the same. The two of these are kind of the same, and so it's easy for me to just change them ever so slightly. So let's practice using this one. We would take the derivative of the first times the denominator, and then minus the numerator times the derivative of the denominator, and your denominator is squared. And we're going to leave the denominator squared like this. We're not going to expand that out at all. We'll just simplify in our numerator. So if we take our derivatives, that'll be 3, and there at the end, the derivative of that quadratic would just be 2x. We'll distribute and then carefully subtract both terms. And that would be your final statement. That is the derivative of this function. That is a rational expression, which is two functions that are divided, two polynomials. Alrighty, here we go. Let's find this derivative and simplify if possible. So that means we're going to take the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. If you want to pause the video and try to do this, I would encourage you to do so. All right, so this first would be 6x squared plus 8x. That would be the derivative of the numerator. And then there at the very tail end, the derivative of the denominator is just 1. So it's going to be pretty easy here to simplify your numerator. You will multiply the first two polynomials together, and then it'll be minus that second expression there. And now I'm going to carefully combine like terms and finish my simplification. And that would be the final answer. 4x cubed minus 26x squared minus 40x, and then it'll be a plus 7 all over x minus 5 squared. That would be your final answer when you were simplifying after giving the derivative. All right, now here's kind of a more rigorous question. We are trying to apply our understanding of this quotient rule and our understanding of equations of tangent lines. Now, the equation of a tangent line, you have to remember, okay, what are tangent lines? Tangent lines are going to just touch your graph at one point. And the slope of a tangent line is the derivative. And so that's going to be our first step. We're going to find the slope of our tangent line, and that is finding the derivative of your function f. So the derivative would be the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. All right, now this is going to work out nicely because these aren't very high-powered polynomials. It's going to be 1 times that binomial minus x times 1. And that'll be over x plus 4 squared, which is going to simplify to just 4 over your denominator, your original denominator squared. Okay, so that is the slope that is the common derivative. But we want to know at a specific point, at the point -5, 5. Okay, well that means we're going to find our derivative at that x value. Plugging in -5 to our derivative to find the slope at a specific point, which is going to be 4. We're going to have a slope of 4. And we're working with the point -5, 5. So I'll plug that into my point slope formula, substituting in my slope and the point, and simplifying, and that will be the equation of the tangent line to that graph at -5, 5. All right. Now, we're going to go through example 6 together, so if you guys will go ahead and move on. I want to talk about higher order derivatives. What do I mean by that? You can take a derivative of a derivative. And really all that is, we're going to look at some applications because it comes in really handy. This happens a lot when you're trying to determine the rate of change of one variable with respect to another. Like, say you were looking at population growth rates, or production rates, or velocity, or acceleration. And those last two, velocity and acceleration, those are what we're going to work with the most in this school year. You see, the position function is usually given as S. That gives the position relative to the origin of an object as a function of time. That's how you determine position. And it's usually like working on a straight line where, you know, if you're going forward, that's positive, and if you're going backwards, that would be negative. Velocity is with respect to position. The function v for velocity gives the change in position relative to the origin of an object as a function of time. So you're looking at the change in position, and if we're looking for instantaneous velocity, which is, oh my goodness, that is like what calculus was developed partly for. You're looking at the change in position over a very, very, very like infinitesimal amount of time, which is really, if you look at that slope of the limit of that slope as it's approaching, as the change in time is approaching 0, that's really just the derivative of your position function. And acceleration. Okay, acceleration gives the change in velocity as a function of time. So really what you're doing here is you're taking the change, I made a mistake. You're taking the change in velocity, v at t, plus the change in t, and then that should be a v right there, not an s, because it's the change in velocity over the change in time as time is getting just approaching 0, which is really what we're doing there is taking the derivative of your velocity function, which means you've taken the second derivative of the position function. So, wow, that is cool. That is what we're going to be working with and looking in depth into during this unit and the subsequent unit. So, an example here. Let's find the second derivative of the function f. Well, to find the second derivative, you first have to find the first derivative. So let's do so. You can pause the video and try and do that. The first derivative would be 9/2 x squared plus 10x minus 6. And then you'll take the derivative yet again, which would be 9x plus 10. That is the second derivative of f. Aw, see, that wasn't too scary. Let's try another one. If you want to, no, I think I want to guide you on this one. Don't pause the video yet, because look, we are dividing by x. Now you could use the quotient rule, but why? Because you can simplify this. You could rewrite it as x minus 4 minus 5 x to the negative 1 power. And then this is easier to work with because we don't have to work with such a complex rule if we don't have to. So that's going to be 1 because the derivative of x is 1. The derivative of negative 4 is 0, so that just kind of goes away. And you'd be working with a positive 5x to the negative 2 power. Okay, so that was the first derivative. Now the second derivative, you would take the derivative of 1, which is 0, and the derivative of that second term, which is negative 10x to the negative 3 power. Now we don't want to leave our negative power in our final answer here. We'll go ahead and write it in the denominator so that our power is positive, and that would be your final answer. All right, for our next one here, C. This one you can't just simplify. This is a simplified rational expression. We cannot do anything further. So we're going to use our quotient rule to find the first derivative. That would look like 1 times x plus 2 minus x times, that's the derivative of the denominator, it would just be 1. When we simplify here, it would be a 2 in the numerator all over the original denominator squared. So that's the first derivative. And we want to find the second derivative, so we're going to take the derivative of this one. So that would be the final answer. Why don't you see if that is what you can get? All right, so you should have the derivative of the numerator, which is 0, times the denominator, which was x plus 2 squared, and then it would be minus the numerator times the derivative of your denominator, which would be 2 times x minus 2. And so that really becomes, that first product is going to be 0. So it'd be negative 2 times x minus 2. I'm so sorry, that should be a plus 2. My apologies. And because you have a factor in the denominator, an x plus 2, and a factor in the numerator, an x plus 2, you can cancel it out of the numerator and you can remove 1 from the denominator. You can divide out that common, and that'll reduce the power in your denominator to 3, and you'll just have a negative 4 in your numerator. All right, I'm going to let you guys try the last problem. I'm going to encourage you to rewrite it so that you have exponents and you can use your power properties. All right, and we'll check it together in class. If you guys had questions, comments, concerns, please write them down and I will answer them when I see you next time. Thanks.